Namaste viewers, this is the physicist and we have a very interesting problem or a question of electricity and magnetism to be discussed today. And in this question, the setting of the question, it's so interesting that the same setting can be used in various questions of varying difficulties, so that if you understand the question properly, then you probably would be able to answer any sort of variant of the same question that we are going to discuss today. Actually, I've divided this question into 6 parts, consequential parts, so that if we start with the question part 1 and the part 2 will follow from part 1, then part 3 will follow from part 2 and so on. So let's get started, and I suggest that you keep your notebook and your pen with you and work along as we go forth. And also, I need to mention that the same question has been solved in a post on my blog, which is thephysicist.in. Go ahead and check that. I'll provide the link to the specific post, so that you can keep it as an online material to refer to in the future. Let's first read the question out. It says, a uniform electric field of strength E acts parallel to the positive y-axis. A uniform magnetic field of strength V acts parallel to the positive z-axis. A particle of charge q with mass m placed at the origin O is released from rest. Then find out the following. What are the things that we are going to find out? Let's just read the first part. It says the position vector of the particle as a function of time. That means once you release the particle from the origin, which is initially at rest, it is going to follow a path because of the two fields, like E and B, and we have to find the position of the particle as a function of time. We will be going through all the parts of the question, but let's first understand the setting of the question, which is in the diagram 1. So let's just look at the diagram 1. I have actually made the diagrams before I'm making this lecture video, because I want to save your time as well as my time. All right, so this is the setting of the question. It says that if we take the space in 3 axes, one is x, y, and one is z. So what happens is, along the positive y-axis, along this direction, there is a constant and uniform electric field, which is E. All right, and then along the positive z-axis, along this direction, there is a uniform and constant magnetic field B. And this particle here at the origin O, which has a charge q and mass m, we release that particle from rest. That means initial velocity of the particle is 0. So what happens is, the particle follows certain path. In this diagram, as you can see, that the particle follows a curved path, and there is a tangent shown at this particular point here, and there is a velocity vector shown which is along the tangent, and this particular velocity vector is at an angle theta with the positive y-axis, so that the y component of the velocity is vy, which is naturally v cos theta, and then the x component is going to be vx, which is v sin theta. Now we already know that if there is a charge in an electric field or an electrostatic field, the force, which is the Coulomb's force, I have denoted as Fc, is given by Q times E. Okay, and it is in the direction of the electric field. But when you try to find out the magnetic field or the magnetic force, which is the Lorentz force, as we have denoted as Fl, that magnetic or the Lorentz force is always perpendicular to the velocity vector all the time. So we have to understand that if at the point when there is the velocity that is as shown in this figure, you will see that the FL will be perpendicular to the velocity vector v. Okay. Now, since v makes an angle theta with the y-axis, FL will make the same angle theta with the x-axis. Since v makes theta with along the since v makes theta with respect to the y-axis, the FL is going to make the same angle theta with the x-axis. That means the x component of FL, which is you can say that it is FLX, which is FL cos theta, and then the y component of FL is going to be FL sin theta. That's all about the diagram. But first of all, let's just try to understand why the particle tries to follow a curved path. What makes the particle go on a curved path? Why not in any other shape? Why not? Why exactly is this particular trend of the trajectory? And this is going to happen every time you know this experiment is done. Even if you alter the value of E or B, it doesn't matter. The path is going to be similar all the time. Why does it happen? That answer could be found from diagram 2. Let's just pay a little attention to what happens here. I've tried to use the quantities of differential quantities of velocity and the force and acceleration is because the point of using differential quantities is that we cannot, when we see as the entire thing, it becomes a curve, and it becomes very difficult for us to understand at what point of the curve the particle goes through what kind of forces. So when we take a differential quantity, let's say the main reason is if there is a curve and you take a very differential element of that curve, it behaves as if it is a part of a straight line. So it becomes easier for us to analyze the situation. So let's see. At time t equals to 0, as it is shown here. Okay, let me use the highlighting thing, so we can highlight this. So this at time t equals to 0, the particle was here, all right, at this particular point at origin, and we just release the particle. Once we release the particle, what happens is the particle starts to accelerate because there is an existing field which is E along the positive y-axis. That means there is an existing force along the positive y-axis. That force will try to accelerate this particle along the positive y-axis, and acceleration means change in velocity. So starting from 0, the particle will try to accelerate for the, let's say it accelerates for a very small time interval, as you can say dt1. By the time interval has passed, time will be from t0 to t1. So let's just call t1 is dt1. In the dt1 time interval, the particle will gain y velocity, a very small amount of y velocity, from 0 to dvy1. Okay, that's the differential velocity that the particle attains or gains by the time it is t1 in time. Okay, that means the particle has somewhere reached here at this particular point, as I'm showing on the pointer. Now in the meanwhile, when the particle was at rest, its velocity was 0, so there is no Lorentz force acting on it, because when you talk about Lorentz force, it is basically given by the charge times the velocity crossed to the magnetic field. Actually, I've forgotten an arrow to denote that the V is a vector. So the definition of Lorentz force is, let me once again write it in black. So when there is a particle travels with any velocity v, and there is a magnetic field which is present there, the force, which is the Lorentz force, is always, if the particle has a charge q, then it is given by q times v, which is again a vector, crossed to the uh, magnetic field. And as we know, whenever there is a cross product that we are trying to find from two vectors, we have to follow the right hand here, right hand thumb rule. So the right hand thumb rule is going to give us the direction of the Lorentz force. But since the velocity at t equals to 0 is 0, that means there is no Lorentz force at t equals to 0. At t1, which is after a very small time interval dt1, the particle has gained a velocity dvy1. Now, because of dvy1, there will be a small differential Lorentz force, that is, let's call it dfl, and that is being given by q times dv cross b. Now, this is a dvy1, and this is the magnetic field is along, as you can see, the green arrow, that is dv, that is the magnetic field direction. So dvy1 cross b, as given by right hand thumb rule, is going to give us a direction like this direction, which is the positive x direction. That is going to be the force, the Lorentz force, a differential Lorentz force. And because of that, a differential acceleration will be there, a very small acceleration will be there, which is qb by m into dv. So how do you find acceleration from a force? You just divide it by mass, right? So q is there, b is there, dv is there. I mean, since in the cross product it's basically v cross b is vv sine theta, and here theta is 90 degrees, so it is necessarily vv. So in the same way, it is a dvb. So what we have done is qb by m and dv is being simply multiplied here. So that's the direction of the acceleration. But the acceleration starts here. There is no way we can say that the velocity, there is a velocity that has suddenly appeared in the positive x direction, because the acceleration has just started. So let us give the acceleration some time to generate some velocity in along the positive x direction. So in the next time interval dt2, let's suppose this was the dt1 time interval, okay, and let's call this time interval as dt2, because now the acceleration has acted for about dt2 seconds. So let's say that the particle has reached here, that is t2, which is necessarily dt1 plus dt2. At t2, there is again a new velocity. This particle is constantly being accelerated by the electric field along the positive y. So by this time, the y velocity, let's call it dvy2, still a very small amount. But here, since the acceleration has been acting for dt2 seconds, it has now generated a velocity in the positive x-axis. Okay, so now let's call that this x velocity, a very small velocity along the positive x direction, as dvx2. So now you can see that the particle has got two velocities, one along the positive y-axis, one along the positive x-axis. So initially it will have a resultant velocity, let's call it dv, which can be given by the vector sum, which is dvx2 I cap plus dvy2 j cap, okay, where I cap is the unit vector in the positive x, and j cap is the unit vector in the positive y. So that's how we know that the velocity vector, now the very small velocity vector, has got x component, y component. From this moment onwards, the particle is now moving in a curved path. As we will see forth, now that the particle has deviated from the positive x-axis, the next time the Lorentz force acts, the magnetic field will actually generate a Lorentz force perpendicular to the dv vector, and that will not be along the x-axis as it was along the x-axis here. It will be a little bit inclined to the x-axis. Okay, now there will be an angle. So from this moment onwards, the particle starts to travel in a curved path. Now let's go back to the diagram 1 and try to once again recall that, as we have said, if this is a curved path that the particle is taking, so at any point of time, let's draw a tangent to the curve that will give us the velocity here. And if the velocity makes an angle theta with the x-axis, then we have vx is v sine theta and vy is v cos theta. Alright, that's the velocity components. And because the Lorentz force depends on the velocity, so whatever the velocity is, the Lorentz force is going to be perpendicular to it. But again, the Lorentz force can be resolved into two components. One is x component, one is y component. And the x component of the Lorentz force is going to be FL cos theta, because if the vector makes an angle with the y-axis that's given by theta, then the same angle is made by the FL with the x-axis, all right, because it this was the initial situation and this is going to always remain the same. So if the V makes an angle theta, so FL also will make an angle theta. So that's the situation here. So the diagram is pretty clear to all of us now. Now let's move on to the derivation. Now we have to, there is a diagram 3, I think we will come to it a little bit later. That is, we can understand the complete nature of the path after we solve it. Now it's time for us to start solving the problem. Okay, so let's, before we actually move on to the mathematics, let's just first see what kind of mathematical data we already have. So let's call it a boundary conditions. Okay, boundary conditions, because we are going to need these conditions because they are the data that we have. So initially at t equals to 0, that's the boundary. We only have initial boundary. We don't know if there is a final boundary or not, and that is not given in the question. So at t equals to 0, which is the boundary, what we have is x equals to 0 because the particle is at origin, and see, initially the particle is at rest, so it doesn't have any velocity. So Vx is again 0, but the particle initially, the moment when we release the particle, it starts getting accelerated. So Ax along the x-axis, the Vx is 0. It's not. We have to. All right. Along the x-axis, actually, it could be the magnetic field, but since at time t equals to 0, the velocity is 0. Along the x-axis, Lorentz force will be 0 because it depends on the velocity. So ax equals to 0. Yes, as I said, initially y is also 0 because the particle is at origin, and Vy is also 0 because the particle is at rest, and Ay is not 0 because there is an electric field along the positive y, and the moment the particle is released, the electric field will start accelerating the particle by imparting a force, and the force is given by q times E divided by, that is the force, q times E, and when you try to find out the acceleration, you have to divide by the mass, which is Ay is QE by m. So far we know that this is these are the boundary conditions. Okay, we'll come to this particular section later. Okay, that sums up what we have for the question. That sums up the setting at t equals to 0. Now let's try to understand the first part of the question. Now it's time for us to understand the question. Let's go to the question once again. As you can see, the question says the first part is the position vector of the particle as a function of time. What does that mean? Let's see. The position vector of the particle means it's a vector r, which is a function of time, and any vector in space let's suppose it is x-axis, this is y-axis, and this is z-axis. Any vector r, even if it changes with time, can be given by x times I cap, or whereas let me just put everything as a function of time. So if it is x of t I cap plus y of t j cap plus z of t k cap. Alright, that's the position vector given as a function of time. Let us see in this situation, now that the particle always experiences two forces. One is the electric force, which is the Coulomb's force, Fc, and the other one is the Lorentz force, Fl. And as we can see, all the time, the Coulomb force is not going to change its direction because it's always along the y-axis. However, the Lorentz force will be rotating as the velocity vector begins to rotate. Okay, but there is no way we can see there is another force which has some sort of component along the z axis, right? The magnetic field is along the z axis, but the force that this magnetic field generates lies always in the xy plane, or which is the z plane. That means z is always going to be 0. Okay, in the xy plane or z plane, z is always 0. So we can eliminate this one, this particular component, and we can sum that the part 1 of the question. Here is how we are going to address the part 1. Let's say just like part 1, the position vector as a function of time is always given as xt I cap plus yt j cap, because z is 0. Okay, so that's something that we ought to find out. So how do we find out x? All right, what we have is like the conditions that are given in the question, or the settings in the question, they can help us find the acceleration. Okay, as we know, if there is acceleration, that is the total derivative of velocity with respect to time, which is again total derivative with respect to time of the total derivative of distance with respect to time. So you see, if you have acceleration, because you have force, you have acceleration. Now if you have acceleration, you know that the rate of change of velocity is given. Now if you solve this, because that's going to be a differential equation, if you solve it, you are going to get velocity, and then again velocity is basically a rate of change or differentiation or time derivative of distance. So if you integrate that, you're going to get the distance. So if we, instead of just talking about distance or displacement, if we resolve it into x and y, and we take ax and ay along the acceleration along the x-axis, acceleration along the y-axis, and we separately integrate them, we're gonna get vx and vy, then we're gonna get x and y. So that way we can reach the answer. So let's just try to do that. Okay, so let's see what happens. How do we find ax? In order to find ax, let's just say ax is basically nothing but fx, which is a net force along the x-axis upon mass of the particle. All right, and what is the net force along the x-axis? From this we can see that the net force is always going to be, okay, the x component of the Lorentz force, which is Fl cos theta. Okay, that's, since this is Fl and this is Fl cos theta, because this angle is theta, so this is Fl cos theta, and the vertical component is going to be definitely Fl sin theta. But when you talk about vertical direction, you won't have one force, you're gonna have two forces. One is also Fc, which is the Coulomb force, that is QE. We'll talk about this later. First of all, let's just see Fx. We know that that's only the Lorentz force, Fl multiplied by cos theta. Theta is a variable, divided by m. So now Fl, as we know, the Lorentz force is given by QVB. Okay, because V and B, the velocity and the magnetic field, are always going to be perpendicular, because the velocity is going to always be in the xy plane, and the magnetic xy plane, and the magnetic field is always along the z axis. That means the velocity is always going to be perpendicular with the magnetic field. That means always the Fl, the Lorentz force, is always given by, the magnitude of the Lorentz force is always given by QVB, Now if you want to find out the x component, all you have to do is to multiply that by cos theta, where theta is the variable. Now if you sum that up here, qvb cos theta upon m, that is gonna be, okay, what we're gonna do, qb will keep that there, and m will just keep it as a factor. Then we write as v cos theta. But from the figure 1, what is v cos theta? V cos theta, as you can see here, v cos theta is the y velocity. Okay, as we can see, the at any point of time, the velocity vector makes an angle theta with the y axis. Then the y component is given by v cos theta, and similarly the x component of the velocity is given by v sin theta. So we can write it down as ax is going to be qb by m into vy. Let's just write it as equation 1. Okay, now for the y component, acceleration along the y-axis, you're gonna have to have Fy, which is the net force along the y direction, upon m, and then the net force is going to be a vector sum of the electric force, which is the Coulomb force, and the y component of the Lorentz force. So if you know now that the Coulomb force is, that's the Coulomb force, and this is the Lorentz force, that's the Coulomb force, and this is the Lorentz force. So Fy at any point of time is given by f of fc minus fl. Okay, this is fl cos, sorry, that's fl sine theta. Okay, here we have found out that fl, the vertical or the y component of Lorentz force is going to be fl sine theta. So this is how the net force along the y-axis going to be written. Okay, Fy is fc minus fl sine theta. So let's come back here and write it down. Fy is fc minus fl sine theta upon m. Again, fc is something that we already know, which is q times e, minus, again, fl is q vb sine theta upon m. And this thing we can further sort it out as q e upon m minus qb upon m, and then v sine theta, and we know v sine theta is the x component of velocity, as we have found out here. This is the x component of velocity at this particular point we have seen. Okay, that's vx. Vx is v sine theta. So let's just go back and write vx here. Okay, so to sum it up, we're gonna write down the equation 2 as ay equals to qe upon m minus qb by m vx. Let's just box it up. And label it as equation 2. Okay, now we know that this is here the problem is that the acceleration along the x-axis depends on the velocity along the y-axis, and the acceleration along the y-axis depends on the velocity along the x-axis. This is a constant. So that's a problem. These two equations, that the x acceleration and the y acceleration, these accelerations are basically coupled now. Okay, so we have to decouple them. How do you decouple them? What you can do is basically you can see that there is nothing much we can do here for this particular part, which is equation 1. For the equation 2, we know that if we differentiate this equation once again with respect to time, the constant term is going to vanish. All right, the constant term will be 0, and we can differentiate Vx. If we differentiate Vx, it is going to give us Ax, because acceleration is the differentiation of velocity. So once we have Ax, we know that Ax depends on Vy. So let us differentiate this equation and convert the Vx into Ax, and then we can put, instead of Ax, we can put QB by AM Vy in that way. And differentiation of Ay, whatever it is, let's just call it differentiation of Ay. So what happens is, differentiation of Ay is going to be a function of By. That is going to simplify our case. So what we could do, let's just differentiate Ay. So let's just differentiate with time. That is going to, this part is going to be 0. So that is going to give us QB upon M times, if we differentiate Vx, we're gonna get Ax, right? So now let's just call it, if it is Ay, let's just use prime, the Leibniz notation, which is the prime notation. So Vy, what is Ay? What is Ay? Ay is Vy prime. If we note that and then put the differentiation there, is going to be minus QB by M, and then Ax. We just have to put the equation 1 again. Totally, equation 1 can be inserted here. Instead of Ax, we can write QB upon M times Vy. The end result is going to be of this entire operation is Vy double prime is minus of QB by M squared Vy, right? So somehow, if we assume that this quantity within the parenthesis is QB by M, if we equate that with omega, we can rewrite this equation as Vy double prime is minus of omega squared Vy, right? Now for this part, how do you solve that? Actually becomes a very interesting equation, a differential equation. How do you solve this? It's very easy. There is a standard way of solving this differential equation, which I have already described in the post, so you should go have a look at it. But this one can also be solved using the standard method of solution in simple harmonic motion, which most people study in the high school. So how do you do that? In simple harmonic motion, the equation of motion is written as x double prime, which is acceleration, is or not just x2. Why should we confuse with x1 and y? Let's say r double prime, which is acceleration, is minus of omega squared, but omega is the angular velocity or angular frequency. So if it's minus omega squared r, that's the standard equation of motion, which is the differential equation. The solution of that, a general solution, is given by r equals to let's say r max or r0, which is let's say r max sine omega t plus delta, which is a phase constant. We don't know whatever the phase is. Phase basically determines this particular part. Delta is an arbitrary constant. What happens is in case of simple harmonic motion, it is not really necessary that at the moment t equals to 0, the pendulum or the particle which is executing the simple harmonic motion is always at the initial position. It could be very well that the particle could be anywhere along its path. So where it actually is at the beginning of time is decided by this factor, which is delta. So that's why we have put this as a general arbitrary constant. Okay, and then you put the boundary conditions, which the initial conditions that you already have would let you know what the value of these things are. Well, basically, we have two arbitrary constants. One is R max here, the other one is delta, and the exact values are determined by the exact boundary condition specific to the problem that you are trying to solve. So we can use the same technique here and solve it. So what we can write it as Vy is given by Vy max sine omega t plus delta, right? That's the general solution, but we're gonna have to find out the particular solution. So how do you do that? Put in the initial conditions. At t equals to 0, we know that Vy is 0, right? Then that is Vy max times sine of, then omega t will be 0 because t is 0. So all that we have is delta. So since this entire term is equal to 0, that means sine of delta has to be 0. There is no other way, because V max cannot be 0. Okay, if Vy max is 0, that means, you know, the velocity actually never changes, because initially it was 0, it's the maximum value is 0. So that doesn't make sense. The only way it will make sense, if sine delta is 0, that means delta is 0. Then we can rewrite this as one less constant y max sine of omega t. However, we still have to find out what V max is. So if that, we further have to simplify it. How do you find that? We also know that at t equals to 0, ay, the acceleration along the positive y-axis is q times e upon m. That's the acceleration, as we have noted in the boundary conditions up above, right? This particular part, ay is qe by m. So that's the boundary condition we are going to use right now. Okay, so ay is qe by m. However, we have only vy. We don't have anything else. So if we have vy, how do you find ay? You just differentiate it. That implies differentiating both the sides, you're gonna have ay, which is given in the boundary condition as qe by m, is going to be vy max, and then differentiation of sine of omega t is only going to give you omega of cos of omega t. Now, but this particular part, omega t, becomes 0, right? If omega t is 0, cos of omega t becomes what? 1. That means Vy max times omega, just write it as omega times Vy max is q e by m. That gives you Vy max, which is q e upon omega m. But we already know the value of omega. We have just assumed that here omega is qb upon m, right? So we can just substitute that value for omega. So let's just write it as, it's really important that you work along with me, okay, on your own notebook. So q e upon qb upon m times m. So everything cancels out except e in the numerator and b in the denominator, so it's going to be e upon b. So now we know Vy max is e upon b, so we can conclusively tell that for our particular case, as we know, Vy is e upon b sine of omega t. Okay, just let me correct this sign my S looks like an 8. Could be very confusing. Okay, let's just write it as sine of omega t. We can write it as equation 3. Next, we're going to understand what is the velocity along the x-axis, for which we need to find out Vx. First, how do you find Vx? From, of course, Ax. And Ax, fortunately, is given by QB upon M Vy. Okay, Ax is QB upon M Vy. What is QB upon M? Is omega. So basically, it's omega Vy. So Ax is QB upon M multiplied by Vy, which is E upon B sine of omega t, and that simplifies further. Well, only the B cancels out, that means it's Q E upon M sine of omega t. So that's the acceleration. All right. Now acceleration is nothing but time derivative of velocity. So it is d by dt of Vx is going to be QE by M of sine of omega t. All you have to do is to just write it as a differentials only, QE upon M, which is a constant, and then sine of omega t times dt, and we can easily integrate both the sides, and if you integrate dvx, so starting from 0 to a certain value Vx, when time starts from 0 to a certain time t, you are going to find out that it's going to be Vx is, since it's we are using definite integration, we are not going to have any kind of arbitrary constant, which is good. So it is QE by M. Now, when you talk about integration of sine omega to dt, it's always going to be 1 by omega minus of cos omega t, which needs to be evaluated between the limits of 0 to t. Since it's a minus sign, we can just reverse the upper and lower limits. So it's going to be Q E by omega m, and we can write cos of omega t evaluated between t now becomes the lower limit and upper limit becomes 0, which is again, now just solve QE upon QB by M. That's what your omega multiplied by M. So everything cancels out again. Now only E by B is there, but at the same time, for the cos omega t, you have, if you put t as 0, it becomes cos 0, which is 1, and then for time t, it's going to remain the same general term, which is 1 minus cos omega t. So now we can write it down as Vx E upon B 1 minus cos of omega t. So that's the value of the velocity at every point of time. All right. So you've got y, you've got the Vy, and now you have got Vx. So let's just have it as equation. Last one was 3, so this is going to be 4. All right. So now you have both Vx and Vy. Okay. Now let's just take a fresh start here. we need to find x and we need to find y, but what we have is vx and vy, right? So for that, what do you have to do? Since vx is nothing but time derivative of x, and we have it as, let's just which is e upon b times 1 minus cos of omega t. That implies you have to just write it as dx is e upon b times 1 minus cos of omega t times dt. It's totally in differentials. Now you're gonna have to integrate it between 0 to any position in x. This side also from 0 to any time interval t, because it's the variable here is t. Now if you do the integrations on both sides, you're gonna find x is e upon b. Now let's just, this is gonna be something bigger, so you're gonna have to integrate first the 1 times dt, that has to be evaluated, so that is eventually gonna give you t, and then minus integration of cos of omega t is always going to be sine omega t by omega, so it's going to be sine of omega t upon omega. And as you put limits between t and 0 to t, um, that's the 0 is just simply going to make sine omega t as 0, so the only thing would be sine omega t by omega. Try it, you're gonna find the same thing. So now you've got you've got the value of x. So let's just remove the square brackets and put usual parentheses here. I'm gonna box it and label it as equation 5. So we've got x. Now how do you find y? Same thing, just use the vy, which is dy of dt, and that's going to be, where is y? Somewhere found it, which is e upon b sine of omega t, and that's going to be pretty easier. E by b sine of omega t, and then you're going to have to write dy is e by b sine of omega t times dt, and if you integrate it from 0 to any y, from 0 to any time t, is simply going to end up with y is e upon b, and then sine omega, that's the integration is going to give you minus of, well, we can put the minus sign later on. It's e upon b 1 by omega, then it's going to be cos of omega t with a minus sign, and you're going to have to evaluate that between 0 and t, in which case if we reorganize it, it's going to be e upon b, and the omega is nothing but qb upon m times, okay, we just reverse the limits, make the upper one as lower one and the lower one as upper one, so the minus sign disappears. So how do you find that, which is cos of omega t? This thing is from t to 0, and simply cos 0 is 1 and cos omega t is cos omega t, of course. That means y is going to be e times m upon q times b squared 1 minus cos of omega t. So that's the solution that you're going to find as y. So you see, x is a function of time and y is a function of time. So you've got equation 6. So now it's pretty easy to now write down these two things, because you know what is x and what is y, right? So let me just write the answer to the part 1 in which you needed to find. So let's, if you want to write it down as x of t, that's as a function of t, y is also a function of t. So the answer to the part 1 of the question is going to be r of t, which you can write as a vector, is going to be x of t, which is e upon b times t minus sine of omega t upon omega. Let's just put it in the curly brackets. That's going to be the value, but there is an I cap there, plus y. Y, as we know, is em by qb squared, which is, okay, let's just write it down here. Which is em by qb squared times 1 minus cos of omega t, put it in curly brackets, that's going to be j cap, and this entire thing is going to be that's the answer to the part 1. So we've got done that. The other parts of the questions are simply going to come from this first part. So that's what we will be dealing with right now, next up. So let's go back to the question. What is the question asking now? If there will be any double point in the trajectory of the curve, if yes, then will it be a node or a cusp? Okay, now in this part it is pretty clear that we have to trace the curve in order to find the answer. But first of all, there is one thing that some of you might not know. What is a double point? A double point of any curve is basically a point where the curve crosses itself. If there is a curve, it crosses itself. This is going to be a double point. Or if double point is basically a point on a curve where the curve crosses itself or touches itself. Okay, so if the curve simply happens to, okay, this is not how it happens. If the curve just like becomes its own tangent, at this point the curve just touches each other, touches itself. It doesn't cross itself, it just touches itself. So in this case, this point is going to be also be a double point. But here you can see that there are two different tangents at this particular point. There are two tangents to the same curve at a particular point, and this is called a node. But this one here, there is only one common tangent to both parts of the curve at the same point, so this is going to be a cusp. How do you know whether this particular particle will go on a trajectory that will have a node or a cusp? How do you know that? For that, you have to first draw the curve, and that is called curve tracing. So we would be, it's very easy to draw this curve. Actually, it might look a little bit difficult, but the fact of the matter is it's pretty simple, because a curve, how do you find a curve? Because we have, so now that we have to plot the curve, we don't have to be very accurate about it. We just have to find out the general trend of the curve. So first of all, let us see the general trend of x and the general trend of y as individual functions of time. So how do we know that? Okay, first of all, let's just take the first question, first part that has been answered. We are on the second part. So the function of x as a function x as basically x as a function of time is e upon b t minus sine of omega t upon omega. So that's the first part. If you see that the nature of this function of time, which is x, nature of x with respect to time, you can see that as t increases, this function is going to increase. However, there is a minus sign, a negative sign here, and what is in the later part is sine of omega t, which is a periodic function. That means as t increases, x is going to increase without a bound, but the rate of increase is going to change periodically, because sine omega t will have a maximum value of 1 and a minimum value of -1. Okay, so if you plot x versus t, you're gonna have a function like this. Okay, that is going to increase without a bound, but the rate of change is going to be periodically varying. Now if you talk about y as a function of t, that is even simpler, which is me upon qb squared 1 minus cos omega t. And as you can see, since cos omega t is a periodic function, 1 minus cos omega t is also going to be a periodic function, and the maximum value will be when cos omega t is minimum, which is -1. That means y max is going to be 2me upon qb squared, and y minimum is going to be when cos omega t is maximum, which is 1, and y min is 1 minus 1 is 0. Okay, so we understand how it is going to happen. The general nature of the curve is going to be like, first of all, let's see how cos omega t looks like. If you plot cos omega t with respect to time, so how it happens is, if you plot, I have to extend this part. How it happens is, it's going to be 1 here, then it becomes 0, and then it reaches a minimum at this point, and then it goes back again, it becomes 0 here, and then it reaches back to 1. At this point it is going to be, if I draw it properly a little bit better, this is going to be -1 and this is going to be 1, right? So if you plot 1 minus cos omega t, you see that 1 cos omega t cannot be greater than 1. That means 1 minus cos omega t is never going to be negative, right? So when cos omega t is 1, this 1 minus cos omega t is going to be 0, and then as it becomes 0 it becomes 1, and then it rises like this and reaches a maximum, which is let's say this is 2, and this point is 1, and this point is 0, and then falls back again to 0, and then rises again to a maximum value, which is 2 again, then through 1 it comes back to 0, and then it rises again. So that is how 1 minus cos omega t changes, varies with time. So that is how y is going to vary with time. So now combine the trend of x, which is going to increase without any bound, and y that goes from 0, reaches a maximum, then falls back. What is the maximum of y max? We have already found that here. So this is how x, if you plot x and y as parametric function, as we know that the particle is never going to leave the xy plane, so z is all the time 0. Starting from origin, if this is y-axis and this is x-axis, the y is going to rise from 0, reach a maximum, come back to 0, and then start the entire cycle again. Go back to maximum, come back to 0, and then the same thing, same cycle once again. This is how it is going to go, and x is going to increase without bound. Okay, so this thing goes on. So that's something that we have understood. So one thing we need to note here, that at this point y is maximum, this is y max, and if you draw a tangent here, you will see that the direction of velocity, which is totally along the x-axis, and vy is 0 at this point, the point of maximum, because y is maximum, y cannot increase any further. That means along the direction of y, velocity has to be 0. So vy is 0. So that means only one component of velocity exists, that is vx, and that is the total component of velocity. Okay, so we have understood that part here. So now that is general trend. If you want to just verify, this is my hand drawn diagram or plot. If you want to have a pure professional plot, you can use some computer algebraic system like Desmos that I use personally. But the thing is, you can't just plot yt the way we have and xt the way we have. So what we're gonna do, we're gonna normalize things so that we can verify on Desmos if that is going to give us the same curve that we found out. To normalize, let's just assume that E is 1 and B is also 1. Charge is 1, mass is 1. That makes omega, which is q b upon m, that is also 1. So omega is 1. Everything, all those parameters have become 1. That means x is going to be t minus sine t, and y is going to be 1 minus cos t. So that's the parametric function we're going to plot in Desmos. Okay, so let's just go to Desmos here. And plot the thing, which we can just x is t minus sine t. So let's just t minus sine t, comma 1 minus cos t, 1 minus cos t. And for the time range, let's start with 0 and let's go up to 100 seconds. You see the function that we were talking about. So that's how it is going to look like. Okay, so we know we are right. So let's get back to this, and we got the right plot, and in this we can see that there is no node, because as we have already defined, a node is where the curve crosses itself. If the curve is like this becomes a node, because now there are two tangents at the same point. But if the curve is like this, there is only one tangent at the same point where the curve simply touches itself. That's a cusp, and this is a node. Okay, but we're not having any node here. All we have is cusp. So all these points, there would be cusps. Okay, and what is the distance, time distance between the cusps? Like, in what is the minimum time, what is the time difference or time interval between two consecutive cusps? How do you find that? Well, from the equation of y. So y, the time that it takes for y to be 0, the time interval in that y takes to be 0 again, is the same time interval between two consecutive cusps. And what is that? As you can see, the equation of y as we've written, which depends on 1 minus cos omega t, that becomes 0 every time 1 minus cos omega t becomes 0. That means cos of omega t is 1. That means cos omega t is 1 is only when this particular argument omega t has to be 2n pi, okay, where n is 0, 1, 2, 3 to any further integer. That means t is 2n pi upon omega, but we are trying to find the time interval. So for the smallest possible time interval, we can take n equals to 1. That means the time interval between these two, or maybe the same thing happens here. This is delta t, which is 2 pi upon omega. That means this length, the length of x between these 2 points, the 2 consecutive points where y is 0, is going to be 2 pi by omega, which is 2 pi by omega, and the maximum value of y, which is y max, occurs at pi by omega. Okay, so that's something that we have answered. The part 2 has been answered. So now let's move on to the the third part. It says the shortest time interval between points where the particle comes to rest. As we know, particle comes to rest. It's a conservative field for for electric E. Electric field is conservative here, and the magnetic field does not do any work. That means you can also take it as conservative. Usually magnetic field is not conservative, but here it is. So if the particle is at rest here, it is again coming back to rest here again. So how do you know that? You have to find out the equations. Let's verify using the equations of Vx and Vy. So what's Vx? Vx is E upon B times 1 minus cos omega t, and we know that at every cusp Vx is going to be 0, okay, which is 0 at cusp, where and the cusp happens at every time interval of 2 pi upon omega, right? And Vy, if 1 minus cos omega t is 0, which is Vy, then becomes E upon B sine of omega t. Alright, so when 1 minus cos omega t is 0, that means cos omega t is 1. That means omega t is here 2n pi, and at the same point sine omega t will also be 0, definitely. So Vx is 0 means Vy is 0. That means the particle is at rest. That means at every cusp the particle comes to rest, and the shortest time interval between two cusps, or you can rephrase the question as the time interval between any two consecutive cusps would be 2 pi by omega, that we have already found out, right? So that's the answer for the second part of the question, or the third part rather, which is going to be 2 pi by omega. Now part 4, the displacement of the particle along the y-axis when the velocity of the particle becomes parallel to the x-axis for the first time. So in this curve, for the first time, is like if you draw the tangent to the curve, at every point that tangent will show you the direction of velocity, and for the first time the velocity becomes parallel to the x-axis where y is y max. So all we have to do is to find y max. How do you find that? Well, you can actually put the time interval, that is as we know, y max happens for the first time, y max happens when t is pi by omega, right? So you can put in the equation, right, where let's go to the equation of y. Oh, well, we have found out already in this that if you put omega t, or t is pi by omega, you will find y max is 2me by qv squared. However, there is another way. There is a work energy method that we can also use. The logic is that if there is a magnetic field, uniform magnetic field, and that's constant, basically whatever the direction of velocity is, the Lorentz force is always going to be perpendicular to the velocity vector. That means there is no way the Lorentz force is going to contribute to the velocity vector or the net velocity vector. That means the Lorentz force is never contributing to the kinetic energy, since kinetic energy is half of mv squared. Since Lorentz force is always perpendicular to the velocity, it is basically not contributing to the speed. That means it's not contributing to the kinetic energy. So all the time, the only force that actually does some work is the Coulomb's force, which is Fc, which is QE, which is working in the y direction. So starting from 0 to a particular value of y max, okay, so within this displacement, how much work does Fc do? So you know that the Fc, which is QE, is also along the positive y max is along the positive y, so the work done is QE times y max. You can say that, right? And what happens to the work done? It gets converted, because there is no restoring force here. So the total work done basically is converted into the kinetic energy, which is half of mv squared. That means y max is going to be mv squared by 2qe. Now we have to find out the velocity of velocity v, and we know when y is y max, the velocity is purely along the x-axis. So what is the value of x? What is the value of vx? Do we have a formula here written? Here, the vx is basically e by b. So now let's just and vx is e by b 1 minus, well, when you put cos of omega t, you know that when y is y max, at this point, this happens midway, and the entire length of time here is 2 pi by omega, and this thing happens, y max happens at pi by omega. That means cos of omega t is cos omega times pi by omega, which is cos pi, which is minus 1. So 1 minus of minus 1 gives you 2e by b, and that is v, okay, because there is no vy, so vx itself is v. So what you can do is now just plug that in, m by 2qe. Instead of v squared, you can write 4 e squared by b squared. Now you can do some manipulations here, arithmetic manipulations. E is going to take a power, so now it becomes 2me by qb squared. So that's y max, right? That's y max. Now this is the same thing that we got earlier without using the work energy principle, from the simple nature of the trajectory of the path. So y max is 2me by qv squared. So there are two ways in which we can find this out. Part 4 has been answered. Part 5 is the velocity of the particle when it becomes parallel to the x-axis. Well, that's pretty simple. When the velocity of the particle when it becomes parallel to the x-axis, we just did it. What we did it like here. Let's go back to the bottom. Here we just squared it. Here we have found it out. So Vx, when it becomes parallel to the y-axis, sorry, x-axis, that means it happens at pi by omega, and we have plugged that in the equation of Vx, and we found this as 2e by e, right? So that is the answer to this part of the question, which is the part 5. So that has been answered. So 2e by b. And part 6, if the particle will have a velocity purely along the x-axis. It is asking if there is going to be a velocity purely along the purely along the y-axis. Okay, now if the particle's velocity is purely along the y-axis, that means the x component of the velocity has to be 0. That means Vx has to be 0. But as we know, Vx is E upon B 1 minus cos of omega t. What the question wants to know is that whether there will be any velocity Vy which is not 0. Will it happen? Let's see. If 1 minus cos, if Vx is 0, that means 1 minus cos omega t is 0. That means cos of omega t is 1. That means omega t is here. That's omega t, which is 2n pi. And Vy, as you can see, Vy is E by B sine of omega t. See, if omega t is 2n pi, that means at this point sine is always going to be 0. Okay, isn't it? That means Vy is never going to be 0, right? If omega t is 2n pi, that means every time Vx is 0, that inevitably implies that Vy is also going to be 0. You can write as Vx equals to 0. That implies Vy is 0. But you cannot use an implies and implicated by or implies and implied by sign here. You can't use this here, this sign here, because there are points where Vy is 0 but Vx is not. That means here at this point, at every peak, you can see Vy is 0. Here Vy is 0 but Vx is not 0 every point. But Vy is 0, that means Vy becomes 0 here also. Vy becomes 0 here also. At every cusp, Vy becomes 0. And Vx is also 0. At all such points, Vx is 0. Here also Vx is 0. That means the particle comes to rest at every cusp on the trajectory. So there is no non-zero Vy when Vx is 0. Okay, so that answers the 6th part. So basically, by solving these 5 parts, we have understood not just the setting of the question, we have understood how to analyze the setting and find find answers to different questions that can be framed. So with this setting, or maybe a slight variation of this setting, you could face slightly different questions, but most of the questions, I mean, in fact, all of the questions with this setting or any similar setting will be easily solved by you if you have worked along with this lecture and understood everything. If you haven't understood, you can go back to the beginning and watch the entire video again. And if you still have questions, use the comment section, or you can go back to the blog post, and I'll be putting the link in the description, and you can ask a question there, and make sure that you give the feedback by using the thumbs up button, or if you don't like it, give a thumbs down button. All works for me. And if you have something to write in your feedback, you can also use the comment section. Make sure that if you have any further questions that you would like me to make a video on or answer, put that also in the comment section. And or you can actually go to the general physics forum on the blog and put your question there. And That way, I will keep addressing your doubts. In the next video, I'm going to make a tutorial on a very tricky question, which is basically based on this particular lecture. Okay, and you will find how easy it becomes to solve a question when you understand this master question here. So that's in the next video. For now, this is all. Thank you very much, and if you haven't subscribed, do subscribe if you think my videos are useful to you. Or I will put a link of the subscription page on the blog. You can find all sorts of subscription information there and choose whatever you want to subscribe to about the physicist. So that's it then. We'll see you in the next video, and namaskar. Vande Mataram.